Hey class, welcome to lesson 4.7b, day 2 of applications of exponential functions. What we're going to be doing here today in warm-ups is just to review last day's formula, make sure we've got the growth or decay factor figured out, and so that it's not confused with the rate. Just remember, rate is your letter R, okay, which is usually given as a percentage or a decimal in word problems, whereas the factor is your B part, okay? And telling me if it's a growth or decay will depend on if the base is greater than or less than 1, and that's only if you're given an equation. But we're going to take a look at some situations here where you're not actually given the equation, so we need to decide if it's going to be a growth or decay. Let's start with the first expression. We notice the base is greater than 1, so we know that it's a growth. Okay. The factor itself is the part of the formula. The base is given in this case. And the rate, to find the rate, you say, hey, take the rate, it's the base, subtract 1. How far away is it from 1? And you're going to find the rate equals 0.43, which equals 43%. All right. Second example, you'll notice that the base is less than 1, so it's a decay. And the factor itself is 0.86, but how much has it decayed by is when you're trying to figure the rate, you take 1 and you subtract the base. Okay, so that's going to give you 0.14, which is 14%. Okay, it's how far away is it from 1? All right, taking a look at an investment, ladies and gentlemen. An invest, is that going to increase your money or decrease your money? An investment is going to be added interest on, so that's going to give us a growth. Okay. And the 6.5%, folks, is already given as your R. Okay. So in this case, the rate was given, and we have to find the factor. So to find the factor, which is B, you take your rate and you add 1 to it, or 1 plus R. Okay, so that's going to give you 1.065. So when we talk about the factor, we do not give it as a percent. Okay. Taking a look at depreciation, okay. If something depreciates, that means it loses its value, like a car, okay? And when you take a look at depreciation, that means that it's a decay if it's getting worth less value, okay? And again, the rate is given of 46%. So to find out the factor, it's going to be, in this case, B equals 1 minus R. So you take 1 and subtract 0.46, and you're going to get 0.54. All right. Moving on to things that we're going to deal with in a little bit more detail this lesson. It says bunnies population triple. Okay. When they triple, is that a percentage or a fraction? Not really. This is where you actually take a look at the whole factor itself is getting tripled. So that's why B is 3. Okay. Now this can be a tricky one. How do I find the rate from this, ladies and gentlemen? It's going to be B subtract 1. But if you've got 3 and you're subtracting 1, that's going to be 2. So R is really 200% after you times it by, take the decimal part and times it by 100. Now the bunny's triple is going to tell you that it's a growth because it's growing. Okay. The last example here, folks, is called a half-life. And this is something that you may see in science, especially going on to university. And nuclear, think about a nuclear reactor. And it's got some radioactive uranium in it. And a half-life is the time it takes for that chunk of uranium to be half of its weight or half of its mass, depending on how they're measuring it. So the half-life is actually the factor itself. So you could say half, or change it to a decimal, 0.5. And if we're taking a look at the time for it to get half of its weight, is it actually growing or decreasing? It's decreasing, which means it's a decay. All right. And if the rate, we're trying to figure out the rate, and we know that the factor is 1/2. Rate equals 1 minus the base, which is a half. So the rate itself is going to be 50%. Okay. We'll be talking more about half-life in our lesson today. And let's actually get to the lesson. All right. So common applications of exponential functions involve amount of time it takes for a population to either double or be cut in half. So we're talking about double, then the base equals 2. We're talking about being cut in half, that's the base is going to equal 1/2, kind of like what we did in the warm-ups there. Okay? When the factor is given, we use the simple formula y equals a to the b to the x. Okay? Sometimes we must expand on the x when a specific period of time is given, i.e. the doubling time or the half-life time. And we also need to make sure that it's the same units as well. Okay? So I'm going to make sure we put down here same units, kind of like an example we had last day. Just remember though, T is the time, overall time, and D or H is the time it takes to either double or half-life. So you've got to create a ratio there. And just remember, we're going to convert it to function notation. All right. I like to use two different formulas because D tells us we're looking at the doubling time and H tells us we're looking at the half-life. It's easier to come up with a formula when you know if it's either doubling or half. Good. Let's take a look at an example. We're going to start with 30. So what does 30 represent, folks? 30 represents A. Okay. It says that it doubles. What does doubles give us? That gives us the B. And it says every 2 days. So what does that tell us? That tells us that D, because it's a doubling factor, equals 2. And in 10 days past, that gives us the T part. Okay? So once we know we have a doubling equation, we're going to use this one up here. So it's going to be y equals A times B, all raised to the T over D. Okay, let's sub in the information that we know. So y equals 30 times 2, all raised to the 10 divided by 2. You could simplify that in your calculator to 5. Plug it in your calculator. As is, it doesn't really matter as long as you don't make a mistake in simplification. And what are we going to get here? Y equals 960. Because it wasn't given in a word problem, I don't need a therefore answer because we don't even know what 960 is. Okay? For doubling time examples, we had to use this formula, just like we just did. Okay? So now we're changing it to function notation. Okay? So the only difference between this one and that one is we didn't use the right side part, or sorry, the left side part is being in function notation. Okay, and that's where D is the amount of time it takes for the time it takes to double the population. All right. For half-life examples, ladies and gentlemen, we're going to use function notation, but notice the base is a half, but it's T divided by H, where H is the amount of time it takes for the population to be halved. Now, population is a term that's usually used. It could be amount of material. It could actually be number of species. It could be value of bacteria. Okay. So it can be many things there. All right. And again, folks, this is function notation. All right. So let's take a look at putting it all together now, using this little example to get us started with how we interpret the question, using now function notation to create an equation for example 1. So it says here, 1750 gram sample of radioactive material. So what do we know that represents? That represents the A. So A equals 750 grams. And it has a half-life. So as soon as we see half-life, we know that our B equals 1/2, okay, of 23 days. So that tells us our H. So H equals 23. Write an equation to model this situation. So we're going to start at P at T equals 1750 times 1/2, all raised to the t divided by 23. And don't forget, if we're introducing new variables, we're going to say where P at t is the amount of material or amount of future material, if you want to say that. Okay, and that's going to be in grams. Where t, guys, where t is the time. And what are our units for time here, guys? In days. Good. So we've developed a formula that's in function notation from using the model of our exponential. We've just changed it to function notation and using half-lives. B part, determine the mass after 1 year. So that tells us t equals 1 year. But the context of our problem is days. So what we have to do is change that to 365 days. We're going to ignore the whole leap year business. Okay? So what we're going to do, instead of P at t, we're going to go P at 365. My fault. I wrote that in wrong. So P at 365 equals, and wherever you see your t, you're subbing in 365. So 1750 times 1/2, all raised to the 365 divided by 23. And I would recommend you plug it into your calculator just as is. Just remember when you get to the exponent to put a bracket over this fraction. Okay? And when you plug it in, you're going to get 0.029. What does that tell us? Therefore, 0.029 grams exist after 1 year. All right. C part. How long does it take for 1750 gram sample to decay to 10 grams? Sorry, my fault. 100 grams. All right. So what we need to realize is, what does this 100 grams represent? Okay. That represents my P at t. So P at t equals 100 grams. How long? That's what we need to try to find, and that's t. So t equals question mark. So let's plug in what we know. Instead of P at t, I'm going to write 100 equals 1750 times 1/2, all raised to the t divided by 23. Now again, folks, we're going to try to make this expression as simple as possible. So we're going to divide both sides by what term is multiplied by the 1750. So we're going to divide both sides by 1750. And you're going to have 0.057 equaling 1/2, all raised to the t divided by 23. Okay, and again, we're going to try method number 1. Sorry, I'm going to move that down. It's going to cooperate. So method number 1, like we did last day, was trial and error method. Okay, so plug in your calculator and think what we can do. Well, we're talking about number of days. Okay, we already know from the example above that 365 is going to give us 365 days is going to give us 0.029 grams. So you don't need to go that far. But why don't we start with time being 200 days? Plug that in. You get an answer of 0.0024. So that's too far. So let's try t equals 100. Sub that in. You're going to get 0.049. We're getting close. So we plug in between there. T equals 95. That gives you 0.0570. So that's the one we're going to use. Okay. Don't forget we have to compare that. So therefore, it takes 95 days for 1750 gram to become 100 grams. Let's double check our answer to see if it's reasonable. Okay, if we know that it takes 365 days to take 1750 all the way down there, we know that it's got to be proportionally similar, and that seems to fit the model. The other method you could have done, again, we'll see if we can get my graphing calculator up here quickly. See if I can capture it at the same time. Okay, see if it plugs in for me. Hopefully it's coming soon. If my computer, let's see if it's going to open. Oh, here it comes. I have to have some patience. All right, so let's go to y equals. Okay, the first expression we're going to change to 0.057. Oh, sorry, got out of my y equals. 0.057. And the second expression is going to be 0.5 raised to the hat of opening bracket t divided by 23 closing bracket. Okay, let's graph it, see if I need to change my window. Looks like I do, since it's much smaller there. Okay, so window, my maximum for what do I have here? I have my line 0.057, so let's change my y max to maybe, what should we change it to? About 100. Okay, let's see if that helps. So there's my line. Still have to change my window a bit more. Okay, so that's not going to help me. So let's change my y max to, let's change that to 200. And I'm going to change this to about 5 and see if that helps. All right, so here we see the exponential coming along. Okay. And again, it's here. I just have to fix my window so that you can see it. So instead of 0 to 5, we will maybe go 0 to 1 and see if that helps. Maybe that'll help. Let's see. There we go. So now we see our two lines here, folks. Do the point of intersection, just 5. Again, I believe I was mentioning last day, ladies and gentlemen, that when you get to grade 12, you're going to be doing logarithms with it. So if you want to try figuring out your logarithms, that is also viable too. Okay, I'm going to just capture this and hopefully it'll come into my lesson. See if it comes in. Just copy or cut it, take it to our last page, scroll it down. Paste it, bring it over here. There we go. So just put down method 2, graphic calculator. Okay. Question may come up, say, hey, Mrs. R, can we just use the graphing calculator method? The problem is, since we're dealing with so many transformation questions on this unit test, we won't be able to use the graphing calculator, because then you could solve the mapping problems just by plugging on a graphing calculator than guessing, right? So I would recommend that you know how to do the trial and error method. But again, if you're at home trying to figure something out or doing a homework question, by all means, you can use the graphing method. All right, today's homework is page 262, number 6, 7, 9 to 11. Good luck, and remember, we got review next class, and then, or next lesson, and then getting ready for your test. Come see me if you need any help, and have a great day.